Right, so this is 1.2 software and software development, and we're going to be looking at the stages of compilation. So basically, how do we compile a program from source code into an executable file? Like, what are the actual stages? What do we go through step by step? And the first step is lexical analysis. Now, it itself is a two-part process. The first part of lexical analysis simply removes any comments, any gaps, any pointless spaces, which they call white spaces or white areas. So these are basically any unwanted areas are removed. Okay, that's just step one. Nice, easy step. The second step is to convert any keywords into tokens which represent what they do. Now, I've sort of made up some of these. They might not be what they call them. But here you've got an integer, which is a data type, followed by an identifier, which is A, followed by an operator equals, followed by a number 10. Now, of course, the white space would have moved here. And then you can so on and so forth. We've got, number. Then we've got keyword for right line, open para for open parenthesis, got identifier, operator, number, close parenthesis. Okay, so you're turning them into tokens, okay? Because we're going to be doing syntax checking soon. So we want to make sure they're in the right syntax. Turn them into tokens. Next step, we create something called the symbol table, okay? And the symbol table, basically, the Lexa then creates a table which stores the names and addresses of all the variables. Now, I'll be honest with you, it stores more than this. I've simplified it, but it's quite complicated to be fair, obviously. But basically what it does is it essentially goes through all the variables, all the constants, any arrays, and it puts them in a table. Okay. The variables are then checked to ensure that they've been declared and to determine the data type used, right? So there's more than this, but I'm just simplifying it. So here I've only got A. So it goes through the program and it writes a list out of all the things. And that'll be the memory address when running and stuff. Okay. But you don't need to know too much about that. Just know what the symbol table does. It goes through and checks all the arrays and variables and constants and makes a table of where they are and what values they're. Right. Okay. Now we can do syntax analysis. Now we can check to see if the program follows the rules. Okay. So basically, imagine this big table of all the valid combinations of things. Now I've only put 2 in there, and surprisingly enough, it's the 2 that I've got in my program. Wow, it's valid. But imagine I had others in there. Imagine that's an identifier, operator, identifier number. Well, there isn't one in there. So we know that you can't go to state up identifier number. So this would come up as a syntax error. That's basically a list of the combinations of things that could be correct. It doesn't mean if it passes this, it is valid code, but it means if it fails this, it isn't. Okay, because obviously you could still write gibberish, but it could still be correct here, right? So basically it looks through its list, makes sure these things match one of the things in here. If it does, it passes. If it doesn't, it returns, invalid syntax. So that's that bit. Then it goes through. Okay, so often with syntax, you need to define rules. Okay, and you do it with a syntax diagram, but it looks a bit like a flowchart really to me. And essentially, in this example of a postcode, I know postcodes can be very many different things. But I'm going to pretend that postcodes are only 2 letters, 1 number, 2 letters, and then 1 or more numbers. Okay? 2 letters, 1 number, 2 letters, and then 1 or more, because the flowchart can go back, numbers. If it was 1 or 2, we'd have to have a 1 there, and then down here, go to 2 ends. Okay? Then that would allow you to have 2. So if it was 1 or 2, but only 1 or 2, this would be the same, but this wouldn't be here, of course. An arrow would go out here and down from here to 1 that splits, goes number, and then across. So that's how you would do that. Okay, so these are obviously valid. These are valid. This is valid. And obviously these are not valid because, it hasn't got a number. And it must have at least 1 in this instance. And this is not valid because it has 3 letters in a row. Yeah, so there you go. That's the syntax rules. Quite an easy question. I hope it comes up in the final exam. Okay, so after we've done the syntax analysis, okay, you can then create a program that follows all the rules, but isn't actually valid. An example could be, here our program uses an identifier B, but we can see that it is yet to be created. So here, I've done A equals 10, A times B. Now that will work, because it will be, that times that, and that will probably have a version that says times number or identifier. That's valid code if you just look at it, if you just look at it as one line, if we didn't know the rest of the program. But the semantic analysis checks for this and other similar types of errors. So it's basically errors where it matches syntax, but there's other parts of errors like things haven't been declared or etc. etc. So once it's gone through all that process, the machine code will be generated, and this may take a few passes to achieve as the optimization stage will take place. So redundant useless code will be removed, and it will also attempt to replace inefficient code with a more efficient alternative. So for example, below the A plus A minus A would be altered to A, because there's no need to do that. If there was code that was never run, like if there's an if statement that couldn't be possible, it might efficiently remove that. It does lots of clever stuff that I'm not going to go through now, but just understand that it will go through and it will use an algorithm to try and make the code as efficient as possible over many years of understanding the systems, and it will try to improve performance as much as it can. So that's 1.2.2 part 2.